Today we'll introduce a fundamental idea in the study of electromagnetism, Faraday's law, which plays a central role in the application of electricity and magnetism in everyday life. Here's just one example. Anytime you swipe a credit or debit card to make a financial transaction, it's Faraday's law that makes this physically possible. There are many other examples. The charging of a cell phone, the operation of an electric or hybrid vehicle, the generation of electrical power, all rely on Faraday's law. On a more immediate level, you will perform a lab involving Faraday's law. So to help us understand the key physics involved, we'll discuss the setting and context of this upcoming lab, and along the way, gain some insight as to what Faraday's law is all about. The situation we will study will involve observing a falling magnet. In particular, the magnet whose field you investigated in an earlier lab. To be specific, consider a short bar magnet oriented as shown as it falls, with the North Pole in red below the South Pole in blue. As you well know, the magnet exhibits a dipole field. For now, let's recall that on the dipole axis, the magnetic field points away from the North Pole and toward the South Pole as shown. Now, let's consider a circular area, shaded as shown and viewed from an angle, where the dipole axis is perpendicular to this area and passes through the center of this circular area. Now let's note that this surface has an edge, a closed path, that bounds the surface. This will be important for us to pay attention to in a moment. Now, as you would expect, there is a magnetic field due to the magnet on this surface. We will want to calculate the magnetic flux on this surface. We discussed how to do that in general. Remember, we take the scalar product of the B field with the normal vector for each tiny surface area dA, and then add up all such tiny contributions of the magnetic flux to obtain the total magnetic flux at the surface. Now for the particular area we are talking about, the entire shaded area region is oriented in the same way, so there is just a single n hat pointed downward. For the moment, we'll also assume the area A is small enough so that, to a good approximation, the B field everywhere on the surface is the same and equal to the on-axis B field at the surface due to the magnet. Then the integral, the total magnetic flux, is just the magnitude of B on the surface times the area of the shaded region. Now all this is worked out for just a single instant in time. However, we know the magnet is falling, so this picture must be changing in time. Let's see what happens if we keep the shaded area fixed in space and watch the magnet fall. As you can see, as the magnet falls, the B field on the surface, visualized with a black arrow, is changing in time. In particular, in this situation, the B field is getting larger in time, still pointing downward. That must mean the magnetic flux is changing in time as well. Let's discuss how the flux is changing here. We show in this figure the magnetic field at two times, vector B at some initial time t sub I, and vector B at some later time t sub f. Notice that both point downward, but vector B at the later time is larger because as the magnet falls, it gets closer to our shaded area, which is fixed in space. We can compute the fluxes like this, just the product of the area A times the magnitude of the B field at the different times. Now, it will be important for us to find the derivative of the flux with respect to time. For a small difference in time, t sub f, T final minus T sub I, T initial, the ratio delta flux over delta T is a good approximation for this. Let's notice that delta flux is non-zero because delta B is non-zero. That's pointing downward in this case. And notice as well, the ratio delta B over delta T also points downward. We'll return to this fact in a moment. Now, here's the essence of Faraday's law, which is an amazing fact. The time-changing B fields, as expressed by the time-changing magnetic flux, is a source of electric field which exhibits a curly structure. Let's look at a computer simulation to visualize this. As the magnet falls, we see an electric field visualized with orange arrows curling counterclockwise around the edge of our shaded area as viewed from above as the magnetic field, and therefore the magnetic flux increases downward as the falling magnet gets closer to the shaded area. These curly electric fields are described by Faraday's law, which says that the integral of the scalar product of vector E with tiny displacements, vector delta L, around the closed path bounding the shaded area is equal to minus the derivative of the magnetic flux on this bounded area with respect to time. Let's walk through to see how this applies in our falling magnet case. We see the E field curling around this closed path. We discussed how to compute the derivative of the magnetic flux with respect to time. Now, the minus sign in front of this derivative in Faraday's law tells us about how to get the direction of the E field from the flux derivative. As we discussed in this particular case, the magnetic flux is increasing downward in time because the derivative of B with respect to time is increasing in time. Now that means that minus this derivative, minus dB dt, is pointed upward in this case. This is the minus sign from Faraday's law. And here's how we get the direction information. We use another right-hand rule. Stick the thumb of your right hand in the direction of minus dB dt and curl your fingers as shown. If you look at the tips of your fingers, they point in the direction of the curly E field, counterclockwise in this case. That's the essence of Faraday's law. In our next lecture, we'll discuss how these curly E fields can produce currents.